Hello, welcome back. We're going to do 4.3 today. 4.3 actually we're going to do before we do 4.2, so it's a little bit out of order, but that's okay. We have 4 objectives for today. Our first objective is that we are going to evaluate trigonometric functions of acute angles. We're going to use fundamental trigonometric, and I'm going to try to fit this function. So basic trig functions that we learned in Algebra 2. We learned them in geometry. Then we're going to use a calculator to evaluate those trig functions. And then we're going to use our trig functions to model and solve real life problems. Okay, so basically, because today is all right triangle trig, it's going to be SOHCAHTOA, things like that. It's going to be a lot of review from geometry. So hopefully almost everything that we do today should look at least decently familiar. So let's look at our trig functions. So just as a reminder, if I have a right triangle, again, this only works if I have right triangles, okay? The side that's across from the right angle, that is always your hypotenuse, every time, no matter what. The other two sides are my legs, and it doesn't really matter which one is which. Just depends on what angle you're looking at, okay? Side A is always across from angle A. Side C is always across from angle C. Side B is always across from angle B. Okay, so with that in mind, we're going to look at my 6 trig functions. So hopefully we remember these. We're going to do our basic ones first. Sine of theta. Remember this little symbol is theta. It just means an unknown angle. Okay, so sine is always opposite over hypotenuse. Okay, SOHCAHTOA, right? Sine is opposite over hypotenuse. So that's where the SO comes in, right? Cosine here, CAH. So cosine is adjacent over hypotenuse. So if I'm looking at this angle right here, my sine is opposite over hypotenuse, so that would be A over C. My cosine would be adjacent over hypotenuse, so B over C, if I was looking at this angle. And then tangent, TOA, is always opposite over adjacent. So if I was looking for the tangent of angle A, it would be opposite, which is A, over adjacent, which is B. And remember that would change, right? If I was looking then at angle B instead, then my sine would be B over C, and my cosine would be A over C, and then my tangent would be B over A. So they would be swapped there. So it just depends on what angle you're trying to find. Now, these guys are, maybe they're new, maybe they're not. This one right here is called cosecant. Okay, so cosecant is just the reciprocal of sine. So cosecant is just the reciprocal. So this is hypotenuse over opposite. So it's just the reciprocal. Secant here is the reciprocal of cosine. So this is going to be hypotenuse over adjacent. And cotangent is the reciprocal of tangent, so that would be adjacent over opposite. So as long as you know sine, cosine, and tangent, you can find cosecant, secant, or cotangent by just taking the reciprocals there. And that's what this little note says as well. So let's do a quick example. Example 1 here, I just want to find all 6 of my trig functions. The first thing that I notice is that I don't know what my hypotenuse is, right? So that's going to be an issue. So I'm going to have to find the hypotenuse. And because this is a right triangle, I can use Pythagorean's theorem to find the hypotenuse. Okay, so again, the legs, it doesn't matter which one's which. So I'm going to call this one 3 squared plus 4 squared equals c squared. So I have 9 plus 16 equals c squared. So 25 equals c squared. So 5 equals c. So that tells me that my hypotenuse is 5. Now I can go ahead and find all of my trig functions. So let's do sine of theta. So here's theta right here. Sine is opposite, which is 4, over hypotenuse, which is 5. And that's it. Cosine of theta is adjacent over hypotenuse. So here's theta. My adjacent side is 3. My hypotenuse is 5. And then tangent of theta is opposite, which is 4, over adjacent, which is 3. And then when I go to find cosecant, it's just the reciprocal of sine. So that becomes 5 over 4. If I want to find secant of theta, it's the reciprocal of cosine. So that would be 5 over 3. And cotangent of theta is the reciprocal of tangent. So 3 over 4. So hopefully nothing too crazy on this page, just a nice little review of our trig functions and how we use them and all that sort of fun stuff. We are going to get into some more difficult stuff now on the second page. So let's go ahead and keep going. I'm going to read example 2 and then I'm going to scroll down a little bit more. So example 2 says, find function values for 30 degrees. Remember, 30 degrees is pi over 6. 45 degrees, which is pi over 4. And 60 degrees, which is pi over 3. And then this right here, don't forget to rationalize the denominator. So keeping in mind, I'm not allowed to have a square root on the bottom of a fraction. So if that happens, I have to rationalize the denominator. And we'll go over how to do that, or we'll do it together. Okay. So first, let's do 45 because it's the first one written, or it's the first triangle here, and it's here. So, okay. So remember that 45 and pi over 4 are the same thing. So even though this triangle says 45 degrees, it could easily have said pi over 4 as well. But we know that if it's 45 degrees and 45 degrees, the two legs have to be the same. So we're going to call these leg lengths 1. And then if we had done Pythagorean's theorem, we would have found that the hypotenuse is square root of 2. So that's how we got those numbers, okay? So sine of 45, or sine of pi over 4, is opposite over hypotenuse. So I have 1 over square root of 2. But I can't have square root of 2 on the bottom. So over here, I'm going to rationalize the denominator. So by doing that, we have to multiply by whatever the square root is on the bottom and on the top, meaning I'm just multiplying by 1. So root 2 over root 2 is just 1. So I'm multiplying by 1, but I'm multiplying by 1 in a special way. So 1 times square root of 2 is square root of 2. And square root of 2 times square root of 2, the square roots cancel and I just get 2. So this is really root 2 over 2. Okay. So again, rationalizing the denominator just means that you're getting rid of the square root on the bottom. It's okay to have a square root on the top, just not the bottom. So that's sine of pi over 4, or sine of 45 degrees. Now let's look at cosine. Well, cosine is going to be the same thing as adjacent over hypotenuse. And if I rationalize the denominator, I get root 2 over 2 again. Hopefully you can write smaller than I can. So my sine and my cosine of 45 or pi over 4 are the same. And then tangent is opposite over adjacent, which is just 1. So my tangent of 45 is just 1. Okay. Now we're going to do the same thing for 30 degrees. Okay. So here's 30 degrees right here. So we just have to make sure we're following this angle. So sine is, again, same thing here. I'm letting one of my legs be 1 and using the properties of right triangles. I know that this is 2 and this is root 3. So, yeah. So if I'm looking at 30, opposite is 1 and hypotenuse is 2. So it's 1/2. So not so bad. Cosine of pi over 6 or 30 degrees is adjacent, which is root 3 over 2. Again, that's great. Tangent is opposite, which is 1, over adjacent, which is root 3. So now I have an issue because I can't have square root of 3 on the bottom. So I'm going to take 1 over root 3, and I'm going to multiply it by root 3 over root 3. Because I want to get rid of that square root on the bottom. So 1 times root 3. 1 times root 3 is root 3. And then root 3 times root 3, the square roots cancel, and I just get 3. So this is really square root of 3 over 3. And so those are my sine, cosine, and tangent of 30 degrees. Now let's look at 60, which is right here. Okay. So my sine is opposite, which now the opposite is root 3. The hypotenuse is 2, and that's okay. My cosine is adjacent, so 1 over hypotenuse, which is 2. And my tangent is opposite, which is root 3, over adjacent, which is 1. And root 3 over 1 is just root 3. And that's okay, right? It's not on the bottom of a fraction, so that's fine. So these 6 are going to be there's 9. There's 9 things here. Okay, these 9 values are going to be extremely important when we get into unit circle. Okay, so we want to make sure that we fully understand how to find these values, probably even at some point memorize these values and so on, okay? So what I want you to notice here, and you don't have to write this down, but I'm going to draw some stuff, okay? Notice that sine of 30 and cosine of 60 are the same. And same thing for cosine of 30 and sine of 60. They are the same, right? That's because these two angles are complementary. They add to 90 degrees. Okay, does that make sense? 30 and 60 add to 90 degrees. So their sines and cosines are switched, meaning the sine of one is the cosine of the other. And the cosine of that one is the sine of the other, and so on and so forth. So, and that happens anytime that there's complementary angles. So I want to scroll down here. So right here, okay, sine of whatever is equal to the cosine of 90 degrees minus that. So sine of 10 degrees is equal to cosine of 80 degrees. And cosine of 10 degrees is equal to sine of 80 degrees. They can switch. Same thing for tangent and cotangent. Okay. And then same thing for secant and cosecant. You also can do this in radians, but instead of 90 degrees, you just use pi over 2 because pi over 2 is equal to 90 degrees. So using that idea, we're going to find a cofunction. So that's what these are called. These are called cofunctions. So it says find a cofunction with the same value. So sine of 45, the complement angle to 45 is also 45, right? So that tells me that sine of 45 degrees is equal to, and I'm just using this right here, is equal to cosine of 90 minus 45, which is equal to cosine of 45. And we actually just found that up above, right? Sine of 45 and cosine of 45 were the same thing. So sine of 45 and cosine of 45 are the same. And I can do it with radians too here. Just instead of 90, we would use pi over 2, right? So cotangent of pi over 12 is equal to, and again, I'm using this one. So cotangent and tangent are cofunctions. So I know that this is going to be tangent. It's tangent of pi over 2 minus pi over 12. So instead of 90 degrees, I'm using pi over 2. Okay, that's great, but in order to subtract these, I need a common denominator, right? So I get tangent of, if I make this bottom 12, the top becomes 6 pi. Okay, so I just got this first fraction, the pi over 2, to be a common denominator. And then 6 pi minus pi is 5 pi. So I get 5 pi over 12. So the cotangent of pi over 12 is equal to the tangent of 5 pi over 12. So whatever the cotangent is of pi over 12 is the same thing as the tangent of 5 pi over 12. So we just have those cofunctions. Okay, the next thing that we're going to look at is all of the different trig identities. And there's a lot. And so we're going to go through them and hopefully we feel okay about these by the end. But basically, like when we're talking about trig functions are huge, okay? And being able to transition and know that, you know, one thing is equal to another thing or whatever, okay? So I cannot express enough how important this box of information is going to be. Very, very important, okay? These first 6 we should hopefully know. They're called the reciprocal identities. Sine of x is equal to 1 over cosecant of x. Right? They are reciprocals of each other, which then means if I have cosecant of x, I can also write it as 1 over sine of x. So they are reciprocals. I can flip the fraction. Cosine of x is equal to 1 over secant of x. And then vice versa, secant of x is equal to 1 over cosine of x. Again, they are reciprocals. And then we know tangent and cotangent are reciprocal, so this is cotangent of x, which means that cotangent of x is 1 over tangent of x. So those shouldn't be too crazy. So I'm going to go ahead and actually erase those and then scroll down a little bit, just because I think that although those are important, these guys are deserve more space. So, okay, the quotient identities. Oh my gosh, so important. We have to know these. Tangent of x is equal to sine of x over cosine of x. Sine of x over cosine. So tangent of pi over 2 is equal to sine of pi over 2 divided by cosine of pi over 2, or whatever. Okay, and then because cotangent is the reciprocal of tangent, it just is flipped. So this becomes cosine of x over sine of x. And that's really important. We're going to get down to where, hey, I can rewrite tangent as sine over cosine. And use that to help me solve something. Okay, the next one is what we call the Pythagorean identities. Remember that Pythagorean's theorem, right, is a squared plus b squared equals c squared. So just keep in mind it's very, very similar. Notice that it's sine squared of x, and then this one is going to be cosine squared of x equals 1. So if I add those two things together, I get 1. And I want to make a very, very, very important note here, and I don't know if you need to star it or whatever, but sine squared of x is not the same thing as sine of x. Oh, sorry. Go back. It is, I was like, wait, that doesn't make sense. It is the same thing as sine squared of x. Okay, so if I have sine of x squared, it's the same thing as sine squared of x. But it is not, here we go, it is not the same thing as sine of x squared. Right? Notice this. If I have this, that means that the x is the only thing being squared. So these two things are the same. This is not the same thing. So just make sure that we keep that in mind. I don't know if we need to box it or star it or highlight it or whatever, but that's very, very important. And there's more identities that can come from this. So if I have my Pythagorean identity, sine squared of x plus cosine squared of x equals 1. It says I can derive these by dividing by sine squared. So I'm going to divide every single term here by sine squared. Okay. So sine squared of x divided by sine squared of x, anything divided by itself is just 1. So that's 1 plus cosine squared of x over sine squared of x right here. Well, cosine over sine is cotangent. So if I have 2 of those, that just gets me cotangent squared of x, and that's okay to do. And then 1 over sine, I can kind of squeeze it in right here, right? 1 over sine of x was cosecant. So 1 over sine squared would be cosecant squared of x. So there's another identity. And then it says I can do another one by dividing by cosine. So let's go ahead and do that. I'm going to rewrite my Pythagorean identity, just sine squared of x plus cosine squared of x equals 1. And now let's see what happens when I divide by cosine squared of x. So instead of dividing by sine squared, I'm dividing by cosine squared. Well, sine over cosine is tangent. So sine squared over cosine squared is tangent squared of x plus cosine over cosine is just 1. So that's 1. And then 1 over cosine squared is secant squared. So there is another identity. So just make sure that you have these close somewhere. We're going to be using them quite a bit. And yeah, this is going to help you a lot. So keep those nice and safe. Okay, let's look at a couple examples. And we're cruising. Alrighty. Let theta be an acute angle such that cosine of theta is 0.8. Okay. Find the values of A, sine of theta, and B, tangent of theta using trig identities. Okay, so let's do A first. I want sine of theta, and I know cosine of theta. That's all I know is cosine. So I need to look up, and I'm going to scroll up, but it's blank now. And which one of these only has sine and cosine? I don't want tangent or cotangent or anything else in it, because then I'll have two unknowns. Right now, if I just have something with sine and cosine, I will only have one unknown. So the only trig function that only uses sine and cosine is our Pythagorean identity, which is sine squared of x plus cosine squared of x equals 1. So remember that this is the same thing as sine of x squared plus cosine of x squared equals 1, right? It's the same thing. And I know what cosine of x or cosine of theta is. It's right here. So this tells me I have sine of x squared plus 0.8. Cosine of x is 0.8 squared equals 1. Using my calculator, I have sine of x squared. 0.8 squared is 0.64 equals 1. I'm going to subtract that to the other side. So I have sine of x squared equals 0.36. Take the square root, and sine of x is equal to 0.6. It's okay that we used x instead of theta. Doesn't matter. Okay, so basically I didn't want to use anything that had a tangent in it, right? Because I also know that sine over cosine is tangent, and so that one uses both sine and cosine, but I don't know the tangent, so that really doesn't help me. Same thing, like anything else that uses sine and cosine but has other things in it. It's just not very helpful. This is the only identity that has sine and cosine, and that's it, nothing else. So then I only had one unknown that I could solve for. For B, I want to know what tangent of theta is. I'll use theta this time. Well, the good news is now I know sine and I know cosine. And I know that tangent is sine of theta over cosine of theta. And I know what both sine and cosine are. So this should be pretty easy now. My sine of theta I just solved for is 0.6. My cosine of theta I was given, and that's 0.8. And if I get that into fraction form, I get that tangent is 3/4. And that's it. So just using our trig functions to be able to find values here. Last example like this is use trig identities to transform one side of the equation into the other. So what this means is I am going to look at just one side of the equation and I'm not going to look at the other, okay? I'm trying to prove, for example, that the left side equals the right side. So I have to use my trig identities. So here I have cosine and secant. I know that those are reciprocals of each other. So I'm going to write cosine as a fraction, so cosine over 1. And I'm going to write secant as a fraction, but I know that secant is the same thing as 1 over cosine. And I'm not doing anything with the right side. Actually, we don't even need to write the 1, right? We're trying to prove that equals 1 as long as we know that in the back of our head. Well, cosine of theta times 1 is cosine of theta. 1 times cosine of theta is cosine of theta. And anything divided by itself is 1. So I get 1 equals 1. And I have a little check mark, like, yay, we did it. Okay. For B, I have two things and I'm multiplying them together. So let's go ahead and multiply them together. So secant theta times secant theta is secant squared theta. Secant times tangent, so minus secant theta. I can't actually multiply them together, so they just get smushed together. And then tangent times secant is also secant theta, tangent theta. Again, just smush them together. And then tangent times tangent, I have minus tangent squared theta. And this still equals 1. Okay, so I see that these two middle terms get to cancel, so that's exciting. That gives me secant squared theta minus tangent squared theta equals 1. I'm trying to get secant, right? I'm trying to get secant to kind of cancel with this tangent. Using my trig identity up top, I can replace secant of theta. This is the very last trig identity that we did, with tangent squared of theta plus 1 minus. So this was the very last one we did when we divided every term by cosine squared. So secant squared is the same thing as tangent squared plus 1. Well, tangent squared of theta minus tangent squared of theta cancels. And I get 1 equals 1. Woohoo! And I proved it. Nice. We just have a few more problems here. I'm going to clear this and we'll scroll down. We're going to talk about angles of elevation and depression here. Angle of elevation. Now this is really important and I'm going to do my very best to draw. Angle of elevation is an angle formed by a horizontal line and the line of sight to an object. So if I have a horizontal line, like let's say the ground, here's my little dude, and it's usually like to the sun or like to the top of a building or something, right? There's the sun. Okay, the angle of elevation here is coming up from the ground. Or it always has to come from a horizontal line. Same thing with the angle of depression. It's always from a horizontal line. Okay, so that would be the angle of elevation to the sun. If I was looking at the angle of depression, this is usually angle of elevation is pretty okay and kids get it and it makes sense. Angle of depression can be a little bit more difficult. So here we're looking at the sun. Oh God, that was a terrible straight line. I think we usually think it's this angle right here, but it's not. Remember, it always has to come from a horizontal line. So this right here is the angle of depression. Oops, do not want my notes to open. Better. Apparently I can't draw theta that small. So that's usually the tricky part with the angle of depression is it always has to come from that horizontal line of wherever the object is. So it's the horizontal line and it's always below the horizontal line. Okay. So we're going to do 3 examples here of application problems involving right triangle trig. So SOHCAHTOA stuff. It'll be awesome. All right, so example 7 says, a surveyor standing 50 feet from the base of a tree. I don't like that he doesn't have a body, so let's give him a body. There we go. So he's standing 50 feet away from the base. Okay. The surveyor measures the angle of elevation to the top of the tree. So this angle right here is 71.5 degrees. How tall is the tree? So because it's angle of elevation, right, it's from the horizontal up to the object. So here here's my angle, and I have to think about what do I have? I want to know the opposite side, and I have the adjacent side. So what trig function uses opposite and adjacent? Hopefully we said tangent, right? So the tangent of my angle, well, my angle is 71.5, is equal to opposite, well, my opposite is h, over adjacent, which is 50. And I'm just trying to solve for h. So since I'm dividing by 50, I can multiply both sides by 50. I cannot express this enough. You need to make sure that your calculator is in degrees. Okay, if you don't know how to switch your calculator to degrees, of course I don't have a calculator right here. You go into mode and then go scroll down until you find degrees. This calculator is dead, but I can at least show you. Okay, so here's your mode button. Wow, right there. Right next to the second. You go mode, and then you scroll down and make sure that you're in degrees. Your graphing calculator will automatically reset to radians every time that the calculator resets. So you just want to make sure that you're in degrees because they gave you this angle in degrees. If they gave you that angle in radians, you'd want to make sure you were in radians. So anyway, I multiply 50 times tangent of 71.5, and I get that the height of the tree is approximately 149.434 feet. If you did not get that, make sure that your calculator is in the right mode and not in radians. Okay, moving on. Again, why does nobody have bodies? Okay, there we go. You are 200 yards from a river. So here's the river, here's you. So this is 200 yards. Rather than walking directly to the river, you walk 400 yards along a straight path to the river's edge. So 400. Find the acute angle between this path and the river's edge. So the path that you took and the river's edge, so that's this angle right here. What is that angle? So again, we have to ask ourselves, what do we know? I know opposite, right? And then we're assuming that this is the right angle, just so we're clear. So we know opposite and we know hypotenuse. So which trig function uses opposite and hypotenuse? Hopefully we said sine, right? So sine of theta, because I don't actually know what theta is equal to opposite, which is 200, over hypotenuse, which is 400. And I don't really like big numbers like that. I mean, you can do it, but I'm just going to change this to 1/2, right? I'm just going to reduce the fraction. And I want my angle. So I'm going to have to take the sine inverse. So hopefully we remember that from geometry. I cannot divide by sine, okay? But what I can do is take the sine inverse, right? The sine inverse of both sides. These cancel then, and I'm left with theta is equal to the sine inverse of 1/2. And when I enter that into my calculator, I get theta is equal to 30 degrees. And this right here, hopefully we will get to the point where we can recognize did I just spell recognize wrong? Yeah, it's okay. Recognize this from our angle facts, right? So sine of 30 is 1/2, and we did that on the second page in these notes today, right? Sine of 30 is 1/2. So hopefully we'll get to the point where we're like, sine of what is 1/2, and be able to recognize that that's 30. If it's one of those 9 special ones that we will eventually memorize. Okay, last problem here. Example 9. Find the length C of the skateboard ramp shown in the figure. Make sure your calculator is in degree mode. Again, you're given the angle in degree, so it has to be in degree mode. So what am I given? I'm given opposite, and I want to find the hypotenuse. So again, that is sine. So now I have sine of my angle, which is 18.4, equals opposite, which is 4, over hypotenuse, which is C. The only thing I can do is I can multiply both sides by C and then divide. So let's do that. C times sine of 18.4 equals 4. And then I can divide everything by sine of 18.4. And then these cancel, right? And I get C is equal to 4 over sine of 18.4. The other trick is right here when you have sine of 18.4 equals 4 over C. If your variable's on the bottom, you can just switch these two. And that just gets you C over 4 times sine of 18.4. So that's kind of the shortcut, is just know when your variable's on the bottom, you can just switch it. Anyway, I enter this into my calculator, and I get that C is approximately 12.672 feet. Not so bad. Hopefully we're feeling okay here. If not, please make sure that you reach out. We're gonna need to be able to know our trig functions pretty well. So if something's not making sense or we have questions or anything, let's make sure that we reach out and ask for help. I'll see you guys soon.